Here's an introduction to two straightforward KSP problems that are very common. So determine the KSP of calcium fluoride given that the molar solubility is 2.14 times 10 to the negative fourth. So what it does is it tells you that the compound CaF2 has that as its concentration. Translation, that's how much has dissolved. Well, how much and what are we talking about? So first, when we're talking about a salt, we are talking about the solid breaking up into its individual ions. So that is a balanced equation. When it has a charge, we would say that they are AQ. So what is KSP? Well, it's an equilibrium expression. So if I were to ask you to do any equilibrium expression, you'd write K equals products over reactants, and you would only include the aqueous and the gaseous species. So in this case, I'd have Ca2 plus, I'd have F minus, and then I'd have a 2. And in this case, what we call this is the solubility product. What is soluble of my product? So in this case, if we're talking about my equation, and I want to know what the KSP is, what we can do is think about an icebox. So I should have probably written this to the side. But if I rewrite this quickly, and there are many ways that you can approach this, but one of the easier ways to do this is think of it this way. So this is a solid. You're not going to have any of it. But in the beginning, before it breaks up, you don't have any ions. So then if it's going to eventually dissolve a little bit, it's going to drive it to the right. So this would be a plus X and a plus 2X. So I'd have X and 2X. Okay, well, what is my solubility product? It's what the concentration is of the individual ions. Well, this ion is a 1-to-1. So the X is very important here. I'm going to assume that X is the 2.14 times 10 to the negative 4. So in that case, this one's doubled. So this is 4.28 times 10 to the negative fourth. So now I can plug those in to my equilibrium expression. And I calculate that out, and I get 3.92 times 10 to the negative 11th. All KSPs, or most KSPs, will have a very small number because these are not extremely soluble. So when we have a very small K, as a reminder, that means that it's more reactant favored than it is product favored. But that is the relationship of how much of my ions are going to dissolve based on the molar solubility. Take a look at one more example. Another very common problem. Instead of searching for the KSP, now I want to know what is the molar solubility. So very similar kind of an idea. So when I have lead 2 iodide, I would have PbI2 as a solid. It would break up into PbI2 plus and I minus. Okay, so again, if we talk about this in terms of an icebox, I start with nothing. All right, so this is plus X, plus 2X. I have X and 2X. Now in this case, I don't have a molar solubility, but I do have a K, so I can plug that in to my equilibrium expression. Like before, if I know if I don't know a K, I need to know these values to solve for a K. If I know K, then I won't know these values in the beginning. So if I look at this, and I was asked what is my KSP, I hope that you would start to say that it's the concentration of lead times the concentration of iodide to the second power. So let's talk about this. What it's going to look like is this is my X, 2x squared equals my Ksp. So now we can derive this out. So I'll really break it down. So here's my x. This is all squared, so it's 4x squared equals my Ksp. If I combine these two together, I'm going to add another x to that. Right? If I divide by 4, I'll get that, right? And then how do I get rid of an exponential 3? Well, it's cubed, so all I'm going to do is take the cube root. X is going to equal 1.52 times 10 to the negative third. That'll be molarity. And X, when it's a singular X, that relates to the solubility of my compound because that's a 1-to-1 ratio. So this is my molar solubility. So those are two real straightforward and basic questions that come up with Ksp problems.